Hello, good evening. I'll scratch that. Good morning, whatever time you're watching this. I do it every time, but it's because I just, at this point, right, being locked under, kind of being in the house, under stay-at-home orders, right, in my basement where there's no windows, it very well could be the evening, could be the night, could be the morning, I don't really know. The days pretty much all blend together. But, anyways, the exam which you guys took and which was due on Sunday, I hope to have the grades up in the next couple of days. This being the first time the exam's been online, I just want to double check everything, kind of make sure that all the questions populated correctly and answer choices. I just want to double check and make sure everything was done properly. So those should be up within the next couple of days. And so where we are going to get into is, again, we see chapters 26 and 27. I kind of combined the two of them because they deal with the urinary system and fluid-based balance. And really, when we talk about fluid-based balance, the urinary system is the main player in achieving that, right? And we say fluid-based balance, okay, fluid, just the volume of fluid within the body, right? That, by and large, is the urinary system's responsibility. We talk about base, right? We talk about like acids and bases and the ability of our body to regulate how acidic or how basic the fluids of the tissues are, right? That, again, that not solely belongs to the urinary system. The respiratory system also does play an impact in regulating our pH balance, right? If you'll remember way back in 121, probably 7 months ago, anyways, at this point of when you would have come out, 6 months ago, from when you would have covered this particular system, when we eliminate CO2, or when we exhale, right, we eliminate the CO2. If we didn't, right, if we weren't able, or if we didn't exhale sufficient levels of carbon dioxide, that would cause the blood to become acidic. Now, in saying that, it's not like, oh, all CO2 is bad. Nope, not at all. It's not the case whatsoever. Right? CO2 is just as, right, low levels of CO2 are just as detrimental as low levels of oxygen. Right? Correspondingly or responding, if we were to look at high carbon dioxide levels or low oxygen levels, your body would have a much faster and a far more robust response to elevated levels of carbon dioxide than it would to low levels of oxygen, and vice versa. If there were low levels of carbon dioxide, your body would respond much more so and much more accordingly, because of the fact that CO2 is paramount to our body's ability to regulate pH. Right, around 70-ish, we'll look at this later on, but around 70-ish% of the CO2 that our body produces goes towards maintaining the appropriate pH of the blood, of the fluids. Right, a very small amount of it's actually eliminated through the urine, and a very small amount of it is actually eliminated through the oxygen. The vast majority, 70+%, your body actually retains. So this fluid, the stuff that we're talking about, remember, when we talk about fluid, right, it can be one of two places: inside of the cell or outside of the cell. Right? Like, you're either in your house or you're out of your house. There's no third way about it. Right? You're either indoors or outdoors. There's no third way about it. Same thing with the fluid. It's either inside of a cell, right, or it's outside of the cell. Now, we can break these things apart, or we can break apart kind of where the fluid is. Right? So, for instance, if we were to look at extracellular fluid, or the fluid outside of the cells, it can exist in one of three places: in the blood as plasma, right? That liquid this is going back to 121, right? That liquid portion of the blood that the cells and all of the electrolytes are dissolved in. Well, the cells aren't dissolved, but all of the electrolytes, all of the ions, they're suspended in the fluid portion. That fluid portion is the plasma. Same thing with the cells. Those cells travel in the fluid portion of the blood. That is the plasma. Awesome. If I then take that liquid, and if it leaks, which it is supposed to, blood vessels are naturally and inherently leaky, that's okay. But when that blood vessel, or when that fluid leaks from the blood vessel and into the interstitial fluid, again, this part here, that's the interstitial fluid. Right? This all in through here, that's all interstitial fluid. It's not within the bloodstream. Right? It's not inside of the bloodstream, but yet it's not inside of the tissue. It's not within the cell. So it's kind of in that in-between, or the interstitial. Right? Excuse me. And then when the actual tissue, or the fluid, is inside of the cell, that's when it's called intracellular fluid. Now we see highly regulated by electrolytes and protein concentrations. Yeah, this is why, right, a little bit later on we are going to look at it, but this is why our blood is as filtered as it is, right, around every 45 or so minutes. Right, the entirety of our bloodstream, right, has been filtered through the kidney. And why is that? That's because there is an enormous amount of, well, there's a very fine line for which these ions, electrolytes, protein levels can kind of fluctuate. Right? For instance, pH, right, our blood pH, somewhere between 7.35 and 7.45. That's a very small range. Right? So depending on the concentration of these ions, depending on the concentration of these proteins, that in part is what's going to drive the movement of the fluid. Right? What actually, all right, so plasma that's within the blood, some of it has to get into the interstitium, and then from the interstitium it goes into the cell, or vice versa. Right? Fluid that's in the interstitium has to go from the interstitium, or from the interstitial fluid, and enter into the bloodstream. What regulates this? How is this controlled? It has entirely to do with the electrolyte concentrations and the protein concentrations. So that's what we're going to look at, right? Because we have to understand that in order for our kidneys to be able to filter the blood has to get to the kidneys. I know, profound statement, I get it. Right, but any fluid that you want filtered by the kidneys has to make its way into the bloodstream. If it's in the interstitium, that's where it's going to remain. Right? If any fluid in here, right, if that's where it is, that's where it's going to remain. Where your kidneys cannot, quote unquote, get to it here. Right, so this is where people who have like severe edema, elephantiasis is a little bit different, but people who have like kidney disease, or whatever renal disease it happens to be, they develop significant edema. And what that essentially is when they just start to become very swollen. They start to exhibit something called pitting edema, right, where literally you push on your own skin and let it go. Okay, there's a whitish mark that appears and then it slowly fades. That's not what I'm talking about. I'm talking about you push into your, the back of your hand, push into your forearm, and as soon as you release the pressure, alright, your skin pretty much snaps back to its original position. People who are edematous, there's different levels for sure. But let's say the more severe it is, the more significant this will appear. You then push into the back of your arm, for instance, or the back of your palm. You start to displace the fluid in the interstitium, and then when you release that pressure, right, instead of, let's say if you stop pushing on the back of your hand with your thumb, you can see a very pronounced, a very significant kind of divot, right, in the skin. And after a few seconds, after 10-15 seconds, eventually it starts to smooth out, right? And that's an example of where fluid is remaining in the interstitial fluid, or when the fluid is remaining in the interstitium. And remember, if it's in the interstitium, your kidney cannot get to it. Your kidney cannot filter out any excess fluid. So if there's excess fluid in the interstitium, right, this interstitial fluid, right, that's where we start to have edema and those sorts of things. So we see. Right? So the fact that this is so well regulated via the electrolytes, the ions, the proteins, that's the first thing we're going to look at. Right now, don't panic. Right, this here again, this square, this is just a cell, because there are square cells in the body. I guess cuboid shaped cells are sure, right? But right, this here, okay. Here's a cell. This hash line is the blood vessel wall, right? Capillary wall, blood vessel wall. All right. Some important things here. Sodium. All right. Is sodium the only ion in the blood? Nope, not by any stretch. Not by any stretch of the imagination. However, is it the most abundant? Absolutely. Right. So when we talk about electrolytes, when we talk about the movement of electrolytes, sodium is so commonly referred to as the example. And it is just that, right? It's an example. It's not the only ion. However, you can see greater than 90% of all of the ions in the plasma are sodium. Right? So if something makes up 90% of something, right? If sodium makes up 90% of all the ions in the blood, well, we're just simply going to talk about that because obviously it's the most important because of just the sheer sum of this sheer number and concentration of it. All right. So why is this important, right? So sodium is the predominant ion. So due to this, it regulates H2O between the intracellular and extracellular fluid. Well, yeah, remember, water is a follower, right? As amazing as water is, it is a follower. Right? If I have a membrane here, sodium is here, sodium crosses the membrane, guess what water does? Oof. Slow down, there we go. Water follows. Right? Water is the ultimate equalizer, right? If you want to think of it that way. Right? So, due to this, it regulates H2O between the intracellular fluid and extracellular fluid. Well, yeah. Within the cell, right, we're going to look at this one thing right here, right? Potassium, K+, that's the predominant intracellular ion. So inside of the cell, it's not quite 90 plus percent, it's high. It's 80, 85%, right? It's quite high. Potassium is by far and away the most abundant intracellular. Sodium is the most abundant extracellular. Okay. So let's just, good Lord, I'm going to talk about diffusion yet again. I wish this guy would just get off diffusion. I know, but it's just that important, right? Diffusion and osmosis, right? Which is kind of like specialized diffusion of water. Right? when we think about, right, a sodium, let's just draw it all the way around here. Sodium. 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 Cool. If there's an abundance of sodium surrounding the cell, what way does it want to travel? I'll give you 8 seconds to think about it. Yeah. Remember, diffusion is when a molecule goes from an area of high concentration to low concentration. So if 90+% of the extracellular ions in the plasma are sodium, it's going to want to rush into the cell. Right? What follows? Water follows. Who knew? Right. Now, right where we're at. Remember we got to talk about the nervous system, right, from a couple of weeks ago, 2 months ago. Remember, there's a sodium-potassium pump, right? As sodium rushes in, the sodium-potassium pump kicks out the sodium. Right, you remember that? Right, that's in order to maintain the resting membrane potential. Whew, man, I've gone off on the deep end here. Remember the resting membrane potential, right, around -70 millivolts? God, he's trying to tie things together right now. What a jerk. Right. Remember, the cell has a charge of around, we can't forget stuff that we learned previously. Right? Well, excuse me. We can't forget stuff that we never learned to begin with. But we certainly don't want to forget the stuff that we initially did learn, right? But remember, the charge of the cell at rest is -70 millivolts. Right? If that cell remains at -70 millivolts, awesome. We're going to remain at rest. But as soon as it starts to, its charge becomes more and more positive. So once it reaches threshold of around -55, that's when the cell depolarizes and it generates an action potential. That's all review, hopefully. All right. So we're not going to go back into that whole process again. But one of the other things, clear this stuff off here. One of the other ways we see regulates H2O between intracellular and extracellular fluid. Well, let's just say if there's, and I'm just going to draw 1 sodium because I'm not going to bore you by drawing 9 more. Let's say there was, 1, 2, 3, 4. Let's just say there was 4 sodium. Right? Because of that, water would be drawn out of the cell, right? But sodium is entering into the cell, so water re-enters the cell. But now sodium's kicked out because of this pump. So as sodium's kicked out, water follows. And you're like, oh man, this cycle just seems like it's occurring nonstop. Absolutely 100%. Because guess what? If you ever wonder, well, how do ions, how does chloride, how does potassium's already there, how do chloride, how does different minerals, how is it different chemicals and molecules get into the cell? Right, sure, with the endocytosis, right, things like that, but just as far as different solutes that are dissolved in the water. Oh man, ready to blow your mind. Maybe not, but to blow my mind. But I can live with that. Alright. Let's imagine, okay, let's just use chloride for example. Alright. So remember how I mentioned sodium rushes in, so then water follows. Because of the sodium-potassium pump, this sodium is just kicked back out. And what follows? The water follows. Well, these solutes, for instance, chloride, calcium, they're just simply dissolved in the water. So guess what happens, right? This chloride is now in this fluid. So when this fluid now gets reabsorbed because of the fact that the sodium simply gets reabsorbed or diffuses back into the cell, sodium gets diffuses back into the cell, this water, which has now the chlorine or the chloride ion in it, is also reabsorbed back into the cell, and this cycle just continues on and on and on. All right, I hope that makes sense. Okay. So, the primary determinant of H2O's presence in the plasma or the interstitial fluid are the plasma proteins. This regulates H2O between plasma and the interstitial fluid. What the hell did he just say? All right, let's break that down. All right, so when we talk about sodium, all right, up here, that's intracellular, right? Is it here or is it here? Right, that's what we're talking about for sodium. Okay, now, whether or not, the fluid is here in the plasma, right? Remember, this hash line is the capillary wall, right? So anything from basically here to here is in the capillary. I'll just write blood vessel. Excuse me, I'll write BV. Right, BV. Right. So what determines that are the plasma proteins. Right. Proteins are large, and they're negatively charged. But they're large. Let's just imagine, all right, if I do this one little red dot, you're like, oh, it's tiny. It's up here by the top. Can that fit through here? Yep, sure. No problem. No problem. Let's say I'm a protein. Oh, man, is my keister fitting through that? No chance. So I have to remain in the blood. Alright, well, if the plasma or if the proteins remain in the blood, what's that going to do to the fluid? Right. So the H2O here, if more sodium if for instance, let's say sodium crosses over, what follows? Oh, water follows. Okay, cool. As water follows, or as water crosses the blood vessel wall and it enters into the interstitial fluid, what's going to happen to the localized concentration of proteins in the blood? It would increase, right? Right, because think about it. If I've got 5 water molecules, whatever, take 5 pieces of, I'm going to think of an analogy, but whatever. Think if you've got 5 water molecules in one hand, you've got 5 protein molecules in the other hand. If I take 2 of the water molecules from my left hand and just drop them on the floor, okay, they no longer exist. What do you now have a greater concentration of in your hands? Proteins. Right, so that concentration difference, there's something called onconic pressure. We will get to that in a little while. Right? But essentially what happens is, because, remember I mentioned a minute ago, water is the ultimate equalizer. Water wants to make things, right, wants to make things equal. So water, because plasma concentration levels start to increase, water crosses back over, and now that, where in the example, if we had 3 water molecules in one hand, 5 in the other, if water crosses back over, or you pick up the 2 that you dropped, now you've got 5 and 5. Now the concentration levels are equal. Does that make sense? This is where people who have renal conditions, renal pathology, they start to have issues, right? Even people who have liver disorders, cirrhosis, fatty liver, etc. A lot of these plasma proteins are created in the liver. So if you have a difficulty or an inability or some problem producing these proteins, you're going to have issues at this level. Same thing with if you have your renal failure or some sort of renal pathology. At the level of the kidney, if we start to eliminate elevated levels of proteins, that's where we can start to have significant amounts of edema build up. We'll get to that. Maybe we'll get to that today. We'll definitely get to it next presentation, if not today. Right, does that all make sense? Right. So that again, that's the clip. I mean, that is the urinary system in a very, in 25 minutes. Now, all of the steps, the processes, all of the concepts, the important things which go behind that, that's where it can be really kind of, that's where it gets fun and interesting. There we go. So, we see, issues with ion concentrations lead to inappropriate distribution of water. So again, renal disease leading to edema. Yeah, we just talked about this, right? So if in just normal, happy, hunky-dory, normal, appropriate levels, right? Something called normal osmolality, right? If you remember, geez, we're going back to chapter 2, I believe. So we're talking back in like end of August, beginning of September. Right? There's hypotonic, hypertonic, and then iso. Iso just means normal, no change, no difference. So that's just normal. Cool, awesome. Now, when we start to impact fluid levels, right? Let's just imagine if more water went from the cell and it left the cell and it went into the extracellular fluid, what would that look like? Oh, we'll grab a water balloon, fill it up, then go over to someone you don't like. So like your wife or your husband or somebody, right? Or one of your kids. Right? I'm just kidding. I love all those people. Most of the time. A little less so this whole stay-at-home order thing, and now that I'm going to teach my kids math, I'm pretty sure, I don't think math is supposed to work the way that it does nowadays. But anyways, when the H2O leaves the cell, the same thing that happens to that cell is that water balloon that you let all the water leak out of. It gets all kind of shriveled and wrinkled up. Right, that's an example of a hypertonic change. Right, where the cell becomes dehydrated and it starts to, again, not quite as like a raisin, but think of a raisin being kind of a dehydrated grape. Now, let's say the opposite. If excess or elevated levels of water go from the extracellular fluid into the cell, what happens now? Well, just what happens if you just keep on filling up the water balloon. It swells and swells and swells. That's what happens to your body cell. It becomes very edematous. That's an example of a hypotonic change, right? This big swelling cell looks like a big O, right? Hypotonic. Right? Issues with distributions of ions, even issues with distributions of proteins, can lead to problems with where this water with where the water is. Is it in the intracellular or is it extracellular? Again, that's where renal disease, which if we have some sort of renal impairment, that means we have difficulty regulating these ion levels. That's where it can lead to edema. So this is boils right down to it. This is what actually causes the movement of ions, of H2O, of glucose, into and out of the cell, or into and out of the bloodstream, excuse me. You see, the reasons these concentrations are so important is because they regulate colloid, osmotic, and hydrostatic pressure. Ugh, good Lord. I've already described this a little bit. Here, when I talked about, let's imagine if, right, when water leaves the blood vessel, what happens to plasma protein concentrations? They elevate. Right? Again, take five proteins in one hand, 5 waters in the other. I get rid of some waters, so now I have greater amounts of proteins left in my hand. I have a greater concentration of proteins. So therefore, water is driven back into the blood vessel. I already mentioned that. I didn't specify that it has to do entirely with the pressure that's created. Right? But that is what actually drives that H2O and pulls it back into the blood vessel. And it has to do with these pressures which are generated. Right? The actual pressure from the fluid. Right? The actual pressure from the ions, from the proteins. Right? Another way to kind of think about it, to simplify it now, and we'll go in detail later, is think about a garden, a fireman's hose is easier, right? They are just like flat as a pancake. Well, as flat as a pancake. They are flat, right? They're rolled up, they're super flat. They then unroll them, hook it up to a fire hydrant, and then when they turn that fire hydrant on, what happens? Well, that fire hose, which was super flat, now just engorges and it just dilates, right? It just expands. Why? Because the water inside of it is pushing against the wall of the hose and it's pushing it outwards. Right? Well, luckily that fire hose doesn't have any holes, doesn't allow molecules to move through it. Well, blood vessels are designed to allow molecules through. So depending on, just like in the fire hose, let's imagine if I took a bunch of little pinholes and stuck them in the fire hose, there'd be all these little pinholes pushing water out of the fire hose. If I turn the fire hydrant on higher and higher and higher, you can imagine how more and more and more water would leave the fire hose. That exact same concept can be applied here, right? When you increase the pressure, for instance, the blood traveling through it, more molecules leave the blood. Right? Now, there's much more detail, there's much more nuance to this as far as what generates the pressure, but just keep in the back of your mind, that's the importance of regulating these molecules and the movement of these molecules, because that's ultimately what they're going to do, is to impact the pressure. Just like the heart, just like the lungs, right? The reason why our heart can pump blood, you're like, oh, that just heart muscle contracts and it pushes the blood. The heart muscle contracts and it creates pressure. That pressure then pushes that blood down the blood vessel. Same thing with the lungs. Our diaphragm can increase and decrease the pressure inside of the thoracic cavity or within the lungs. And that change in pressure is what either causes us to inhale or exhale. So we see through the production of urine, right? Kidney regulates volume, osmolarity, acid-base balance. Yeah, blood volume is just simply the amount, right? Blood osmolarity. Think of that as being the concentration. Right? Chemists would yell at me, but for all intents and purposes, just think of concentration, right? Acid-base balance, right? I've alluded to acid-base balance a little while ago. We'll talk more about it in the future. But in order to produce the urine, I've mentioned it a couple of times already, right? In order for our kidneys to be able to produce urine, right, the blood has to get to the kidneys. There's no choice. Right? If the blood doesn't get to the kidney, the blood can't filter, or the kidney can't filter the blood. All right. So the first thing we're going to look at is this blood vessel, or the blood supply. We can see renal artery, renal vein, right, way up in here. We learned this way back in 121. Right, renal artery here, feeding this kidney. Renal artery here is a little bit hidden, but we can see the renal vein right here. Remember, abdominal aorta comes down, right off of the abdominal aorta, left and right renal arteries. Cool. Then feeding back into the inferior vena cava, we have the left and right renal veins. That's all review. Perfect. Now here, right, as the renal vein, or I'm sorry, as the renal arteries feed into the kidney, right, just like we learned in the cardiovascular system last semester, right, all of these, now, no, we are not, I do not expect you guys nor want you to know each individual one of these, right? Ones I do want you to, obviously the inferior, aorta, renal artery, inferior vena cava, renal vein, but when we come down here, the afferent arteriole, the glomerulus, the afferent arterioles, the vasa recta, at that level, that's where the actual urine production is going to occur. Right? That's where we actually start to filter out the blood at that particular level. Again, the afferent arteriole, glomerulus, efferent, and the peritubular capillaries. So how much blood does the kidney actually receive? Right, you can see the kidneys, it's about the size of your fist. Right? Less than 1%. Right? Less than 1% of your body's mass are your kidneys. However, it receives a range between 20 to 25% of your cardiac output. Now that does change depending on activity level. You're exercising, those sorts of things, your kidneys will receive less blood. But right, for at any particular time, right, just sitting there, lying there, talking to people, eating whatever, it receives almost a quarter of your cardiac output, almost a quarter of all the blood that your heart pumps. Now you can see on average, around 180 liters. So if we do the math, which, oh man, it took me, I had to call up Texas Instruments, get a graphic calculator, call NASA, but it turns out, when you do the math, it's around every 45 or so minutes, right? That's how long it takes for your kidneys to filter the entirety of your bloodstream. 45 minutes, that's it. Right? So, every 45 minutes, oh man, 12, so I would say 15 times, 16 times a day. See, that's why I don't do math. That's why I don't do math. That's why I don't do math. Right? But yeah, so again, almost once an hour. Right? So for some reason I was thinking there's only 12 hours in a day. There's clearly 24 hours in a day. But hey, that's where I'm at. So another quarter of that. So around 32 times, right, a day. Right? Give or take. So that's a huge number of times that your kidneys are filtering your bloodstream, right? So because of that, there's different hormones. There's different reasons as to why our kidneys are fitted with different receptors. They respond to different hormones that can help regulate fluid volumes. There's reasons as to why our kidneys releases a hormone called erythropoietin, which stimulates the production of red blood cells. So it helps elevate our ability to carry oxygen around the body. There's a reason why the kidneys are involved with all of this, because your kidneys receive the entirety of the blood supply within less than an hour. Right? So it's a fantastic organ to be able to measure the concentration of the blood. All right. So the concentration of the blood, how I mentioned, this is something which needs to be highly regulated. And there's a structure within the kidney called the nephron. Right? The nephron is not really that big. The nephron is not this size. Right? There's around a million, give or take, there's around a million or so nephrons in each kidney. Right? So no, it is not nearly this large. But you can see, right? We see right here this little bulbous thing, the squiggly lines are really easy to see. They have different structures. Right? There's a renal corpuscle, there's renal tubules. Each part is responsible for a different portion of the process in producing urine. Right? One thing to look at, right? The renal cortex up in here. Right? The renal medulla down through. We can see where the nephron exists, right? The renal corpuscle, proximal convoluted tubule, that exists up within the cortex. The loop of Henle, that's going to dive deep down into the renal medulla. Right? A little bit later on, not today, right? But we're going to look at one of the ways, or how the nephron is able to adjust the composition of the blood. Right? Think about, adjust the composition of the blood, but also adjust the composition of the urine. If you drank an abundance of water, you need to get rid of a large volume of water. Right? If you didn't ingest a bunch of water, you don't want to get rid of as much water. And the fact that your nephron spans through the cortex, through the medulla, one of the things that allows for it is to be better able to regulate the amount of H2O or water, which is eventually lost through the urine. Right? We'll take a look at how it actually does that. So there's two structures which make up the nephron. Right? Again, if I kind of take this guy here, blow it up, right? That's what we're looking at right here. Right? This is the nephron. So there's the renal corpuscle, the structure here, the renal corpuscle, and there's something called the renal tubule. So the renal corpuscle, this guy here, this is what's going to produce what's called the filtrate. Now, don't confuse the filtrate and the urine. The corpuscle doesn't produce urine. The reason why I say it doesn't produce urine is because it produces something which ultimately might become urine, but before it becomes urine, it's called the filtrate, because the fluid that's initially filtered out doesn't look anything at all like what the urine looks like. And I don't mean like physically looks like, I'm saying concentration of molecules and that sort of thing. Right? But that's where, again, the renal corpuscle produces the filtrate. Now the renal tubule here, this functions to modify the filtrate. Yeah, just like the renal corpuscle produces the filtrate, well, the renal tubule is meant to modify. What if there's certain molecules like glucose? What if there's molecules like sodium, potassium, certain amino acids that we want to reabsorb back into the bloodstream? We can do that along the renal tubule. If you're like, oh, that doesn't make a lick of sense, don't worry. That's what we're going to be spending the next 20 minutes. So here, filtrate's produced here in the renal corpuscle. Right. Here is where that filtrate is modified. You can see ultimately your kidneys produce urine. Anything in the urine will be eliminated from the body. But before that, before it becomes urine, we can take and steal and beg and barter, and we can pull things from the tubule and from the duct and reabsorb it back into the bloodstream, because as long as it's in the bloodstream, it's going to remain inside of the body. Right? So the first thing we're going to look at here is the renal corpuscle. Again, the renal corpuscle. one of the arteries, this guy right here, that is the afferent arteriole. The afferent arteriole. The afferent arteriole is going to feed blood into the glomerulus. Now, well, I thought that was the corpuscle. Yeah, this whole structure is called the corpuscle. There's about 10 different separate, right? This is like your house. Inside of your house, there's 10 different rooms, right? Just like the corpuscle, there's 10 different structures inside of it. There's not 10, but you get my point. Okay. So we see here, right? Within the renal corpuscle, this here is called the glomerulus. Right, this tuft of capillary, right here. So as blood comes down into the afferent arteriole and enters into the glomerulus, and it just swirls around this capillary bed. As it swirls around this capillary bed, right, what happens to a fireman's hose that you hook up to a hydrant and turn it on? It swells up. And if there's little pinholes in that fire hose, the water starts to shoot out. So as the blood comes into the glomerulus via the afferent arterioles and swirls around, some of the liquid portion, as well as other solutes, gets pushed out into this space. This space is called Bowman's space, or the glomerular space, or the capsular space. Choice is yours. Cool. So, what gets squeezed out, that's what is called the filtrate. It's not urine, it's filtrate. That's what got filtered out. And you can see there's different structures, different cells. There's almost like little fishbone looking things. Right, those are called podocytes. Those are cells which help to regulate what molecules can and cannot leave the glomerulus. Right, these are the podocytes. All right. Now, the filtrate. It's produced in here. Eventually, it is going to enter into the proximal convoluted tubule. Because remember, once it's from the renal corpuscle, it has to then enter into the proximal convoluted tubule, because this is where that filtrate is then modified. Right? So a little bit later on, we're going to look at, not today, we're going to look at what can impact how much filtrate's produced. What if there's a huge amount of blood which enters from the afferent arteriole into the glomerulus? How does that impact things? Right, we're going to look at that. So here, just to kind of help people out a little bit, right? Blood enters here. Here the blood gets filtered and filtrate's produced. Right? Yeah, through these podocytes, these little fishbone things, those little slits. Those little slits create something called a pedicel. Right? Now the glomerulus, there's pores, there's different what are called fenestrations throughout the glomerulus that permit the movement of certain molecules, H2O, glucose, amino acids, etc. That filtrate is captured in Bowman's space, or the capsular space. Right. Now this thing here, this is called Bowman's capsule. Right, Bowman's capsule. that's going to be important when we talk a little bit later on about pressure. We won't get to it today. When we talk about pressure, right, how much filtrate does this thing produce? Later on, we're going to look at something called GFR, glomerular filtration rate. All right, things that affect the glomerular filtration rate, so the rate in which the glomerulus produces filtrate. Right? All right. So, what affects GFR? All right, a couple of things. How does volume and rate affect this? So, let's just imagine if there is, let's say, if we increase the amount of blood entering into the glomerulus, how does that affect GFR? If we increase the amount of blood entering into the glomerulus, well, think about the fireman hose. If I turn the spigot on just a little bit, it just kind of barely shoots out at the end and it just barely swells the hose. If I crank that puppy up, now the hose is expanded as much as it's possibly going to. So if we increase the amount of blood traveling into the glomerulus, we're going to produce a greater amount of filtrate. Does that make sense, right? So one of the ways we can downregulate that, or we can kind of inhibit that, is if we, through this right here, neural input. We're going to look at this picture in just a second, but just think of it. If I erase 1, 2 of the, if I slow down the amount of blood traveling into the glomerulus, if less blood enters the glomerulus, then I'm going to produce less filtrate. That's the entire purpose to these things right here, something called the juxtaglomerular apparatus, right? Neural input with these sympathetic motor neurons, which impact the size of the afferent arteriole, and then the various hormonal inputs. Right, we're going to look at these things. Now, one of the things is just GFR, autoregulation. If GFR is elevated, then a myogenic mechanism and tubuloglomerular feedback causes the afferent arterioles to constrict, thus reducing pressure. What the hell is he even talking about? Alright. Oops, sorry. I forgot I was going backwards. It's like one slide. Oh, Lord. This right here. This right here. So, I'm going to back up for a second. Okay. Do we see here's the renal corpuscle. Here's the proximal convoluted tubule coming all down through here. Proximal convoluted tubule. Coming down, we have the loop of Henle, loop of Henle, loop of Henle, loop of Henle. Now I'm starting to get into the proximal convoluted tubule. And you look where I'm heading, I am about to cross back past the corpuscle. Right here. And guess what? I'm hunkered down right beside, right, the afferent arteriole. Right? Literally, the distal convoluted tubule crosses directly beside the afferent arteriole. For that reason, that's what allows, there we go, that's what allows, right, the myogenic mechanism, that's what allows the size of the afferent arteriole to change. Let me explain for a second. All right. Let's say elevated levels of blood traveling into the glomerulus. What happens? Okay, it produces more and more filtrate. Okay, it produces more and more filtrate. Okay. that means more and more filtrate has now entered into the proximal convoluted tubule. Okay. Well, at the end of the line, remember how I mentioned on this slide here? Here's the proximal convoluted tubule here. There's more fluid in the proximal convoluted tubule here. It's that much more pressure traveling through the proximal convoluted tubule, through the loop of Henle, through the distal convoluted tubule, and now there's a greater amount of fluid inside of the distal convoluted tubule, which means that's this right here, right? Now this is ascending limb of the nephron loop. That's literally right where the distal convoluted tubule and the nephron loop, like that's right the transition point. So don't let that confuse you, right? But if there's a greater amount of filtrate produced via the glomerulus, that means there's a greater amount of pressure or a greater amount of fluid inside of the distal convoluted tubule. What does it do? It distends the distal convoluted tubule. That's what then, if it distends it, that means there's too much filtrate being produced. So what can happen? These mesangial cells here, these juxtaglomerular cells, contract. And when they do that, it then allows less blood to enter into the glomerulus, which means we produce less filtrate. If we produce less filtrate, that means there's no longer any sort of distension in the distal convoluted tubule. And now everything's right in the world yet again. Right, does that make sense? Alright, so now it's not only based upon the amount of filtrate, but also the concentration of the filtrate. Because I can think of it this way. If there's a greater amount of filtrate being produced, that means we're getting rid of greater amounts of glucose, greater amounts of sodium, potassium, all these different ions. Right, so if we're getting rid of greater amounts of these, the concentration of that filtrate, that too can impact what the distal convoluted tubule does, or whether it constricts the afferent arteriole or not. Okay. So here it has the pressures listed. We're not going to talk about that just yet. I know you're foaming at the mouth. Be patient, right? But this, right? This I just pointed at my computer screen. Right? This here, this is the reason, right? These pressures, right? This is what we're trying to regulate. Because if we are able to regulate the amount of volume getting into the glomerulus, that means we are then in turn going to regulate the pressure inside of the glomerulus. Right. So the only way to regulate the pressure is to first regulate the volume. Right. Now, via sympathetic nerve fibers, right? Let's say in the events of exercise. In the events of increased fluid loss. Right? That's where the sympathetic motor nerve fibers stimulate the smooth muscle of the afferent arteriole, and the afferent arteriole constricts. As it constricts, that means less fluid is traveling through the afferent arteriole. Now, I know somebody just said, well, wait a second, I figured like if the tube gets smaller, the blood travels through it faster. Yes, you are correct. But even though, let's say, the afferent arteriole constricts, which means less blood is getting through the afferent arteriole, this area of the afferent arteriole, blood will travel through it faster, 100%. However, the volume traveling through it is what is important, because the volume has shifted downwards so much, because there's so much less volume traveling through the afferent arteriole. that's what reduces the pressure inside of the glomerulus. Does that make sense, right? This localized pressure right through here, through the afferent arteriole, that will increase a little bit because of the vasoconstriction, but I don't care what the pressure is right there. I only care what the pressure is inside of the glomerulus. Make sense? Okay. Now, the hormones, right? Via the hormonal input. So renin, aldosterone, ADH, atrionatric peptide, these are all different hormones which are going to play a dramatic role in our GFR, or our glomerular filtration rate. Excuse me. We see released by the cells of the juxtaglomerular apparatus is something called renin. Now, here, these juxtaglomerular cells. Do you remember how I mentioned a second ago? Well, 5 minutes ago, 2 minutes ago, sometime in the last couple of minutes. The distal convoluted tubule, as it's traveling past the afferent arteriole, it can impact the size of the afferent arteriole. All right. The other thing I had mentioned is it too can help regulate or measure the concentration of certain electrolytes and ions in the urine. Right? If there is, let's imagine if there's too little ion concentrations in the DCT, that means the urine is too dilute, or vice versa. Right? If it is too concentrated, that means that there isn't enough water. That means we must be dehydrated. Right? So that's where the juxtaglomerular cell can stimulate the release of renin. Renin is a hormone which, at the end of the line, helps to release a hormone called aldosterone from the adrenal glands. Aldosterone, if you remember, released from the zona glomerulosa, it functions as an antidiuretic, and it allows your body to retain fluid. Right, so if, I'm just going to, call it sodium. Right, if sodium levels are elevated, that means we don't have enough water. Well, why that is, we haven't gotten to yet, right? One of the things which not to confuse you, and I may have just, but don't worry, I'm going to fix it. I'm going to hold your hand. I'm going to walk you through it. One of the things to help kind of understand this first, we're getting into the tubule next. Right? One of the ways that your tubule can modify the filtrate, and it can influence the concentration of the urine, is certain aspects of the tubule are impermeable to certain molecules, while it's impermeable to others. For instance, the proximal convoluted tubule, it's pretty much permeable to anything and everything. Right? Really, same thing with this first part of the loop of Henle. The ascending limb here, this is impermeable to water. Water cannot travel through this guy. Right? Water's just stuck where it's at. Water can't enter into this. Alright. This is better. Water cannot enter through this guy. It's impermeable. So this is where, let's say if there was a high concentration of solutes in the filtrate, water, even though because of osmosis, water is a follower and it should dump into the tubule, it can't, because of the fact that the tubule is impermeable right there to water. So, another way that if there's too high sodium levels, right, again, using sodium as an example, right, that's where it, again, can stimulate the juxtaglomerular cell to release renin. Renin being that hormone, which eventually causes the release of aldosterone. Right, we'll talk about the other hormones in a second. But this pathway here, right, reducing blood volume, reduction in blood pressure, right, our kidneys release renin. Our liver is always producing something called angiotensinogen. When renin and angiotensinogen meet, right, they're lovers. Call them a one-night stand, whatever you want to call them. Right? They hook up. They have a baby called increased angiotensin 1. Right? It's the worst affair ever. Oh my God, what am I even talking about? Good Lord, right? But right, they that one-night stand where they ends up having a baby. Right? Renin plus angiotensinogen gives us angiotensin 1. Right? In the lungs, there's something called ACE, which is angiotensin converting enzyme. That converts angiotensin 1 into angiotensin 2. Angiotensin 2, that's going to do a couple things. That's going to stimulate the release of aldosterone from the adrenal gland. The other part is that's going to lead to something called vasoconstriction of the arterioles. Vasoconstriction. All right, so the vessels are going to constrict in size, which if they constrict in size, that's going to increase the pressure traveling through those localized vessels. Now down here we see in the kidneys increased sodium and water reabsorption and increased secretion of potassium and hydrogen. Yeah. Sodium. If we increase the permeability of sodium, that means we reabsorb more sodium. Well, water's a follower. If I reabsorb more sodium, water will follow. Right? Antidiuretic hormone, right? This we talked about in the endocrine chapter. But antidiuretic hormone, that plays its impact is felt along the collecting duct. Right? Again, this guy here. Right, the collecting duct here. Right? Antidiuretic hormone affects the permeability of the collecting duct to water. Right? So let's imagine if the filtrate was super concentrated, what would water want to do? It would want to enter into the collecting duct. But in the presence of antidiuretic hormone, that doesn't allow this to occur. So water cannot enter the collecting duct. It basically bounces off the wall. Okay. Like pounding on the keys here. Okay. So what's the filtrate composed up of? Or what's in the filtrate? Right? We see the composition is pretty similar to that of the blood. Right? We see mainly water with some of the same solutes, minus some of the larger molecules like proteins and cells. Right? As far as the concentration, it's similar to that of the blood. Right? We can see, right, the amount of filtrate produced around 180 liters, and there's around 178, 179 which are returned back to the bloodstream. So you can see there's 99%, 98%, right, of the liquid, right, which is filtered out on a daily basis, gets returned back into the blood. Right. Now, proteins. You see the amount of protein within the urine or within the filtrate, only around 2 grams. There's a small amount of urine, which let's try that again. There's a small amount of protein which makes it into the filtrate, and for a couple reasons, one, I mean, proteins are negatively charged, which impedes their ability to cross the wall, but two, they're quite large. So because of that, that significantly impedes their ability to cross the capillary and the glomerular wall, right? But you can see, right, the vast majority of what is filtered out does get reabsorbed, and you see there's a very small amount of urine of protein in the urine, right? Certain times, right, of life, right, after, let's say, a real traumatic, very significant accident, in puberty, when there's massive tissue growth, first thing in the morning, it's actually really, pretty normal for there to be a small amount of protein in the urine, because that's how much tissue synthesis is taking place through puberty, right? Even earlier on, when there's that significant amount of tissue being produced and synthesized, there can be, elevated levels of protein in the urine, right? First thing in the morning as it accumulates, not like a prolonged, right, significantly heightened level. That's something entirely different, right? Glucose, right? Glucose, we can see how much is filtered out, right? Glucose is something which is significantly filtered out, right? I mean, almost entirely. Now, part of the importance of glucose, you can see via active transport, right? It's actually a symporter along with sodium, but all of the glucose which is filtered out, all of it gets reabsorbed, all of it. I guess I should have drawn it this way, right? The entirety, right? That's how important glucose is. Now, this isn't infinite, right? This isn't like if you are an uncontrolled diabetic and I live at, whatever, a level of 300, right? There is a limit, and that has to do with the fact that your body can only reabsorb sodium. Well, in the tubule, the way that your body reabsorbs glucose is by reabsorbing sodium. We won't have time to get to that today, but that's where we'll start to pick up on next presentation, is talking about the tubule, and we will absolutely get into diabetics and why they have sugar in their urine and that sort of thing. Now we see urea, creatinine, right? By and large, these are waste products, right? Urea does have several functions, right? So we do see there's around half of the urea which is reabsorbed. Creatinine, right? All of creatinine that is filtered out is lost in the urine purposefully, right? So there's no amount of creatinine which is reabsorbed, right? But if cells or proteins were present in the urine, yeah, if somebody had some sort of renal infection, glomerulonephritis, renal failure, whatever happened to be, that's where you can start to have cells present in the urine, or proteins present in the urine, right? If there's a massive infection, well, yeah, if there's a massive infection, it just makes sense there's going to be white blood cells in the urine. Proteins, same things, same idea. If through the capillary wall and the glomerulus, if the holes are usually this big, if because of the renal disease they're now this big, then yeah, protein, which normally wouldn't have fit, can now get right through. Right? So, because of the fact, right, we see the filtrate similarity to the blood, right, it must be modified. Yeah, there's so many molecules, particles, ions, amino acids, glucose that we absolutely must reabsorb. Right? The entire process by which we can absorb them. Right? That's what we're going to pick up with next class. Right? We're going to look at how is it that the filtrate goes through that modification process. How is it that modification process actually occurs? Right, so again, that's what we're going to pick up with on class on Thursday. Everybody, take care. Have yourself a wonderful rest of the day. Get outside, enjoy some of the weather. It's supposed to be rainy for the next, foreseeable future. But, just a little rain. Never hurt anybody unless you're, Wicked Witch of the West. I never saw Wizard of Oz. My wife always, always yells at me. refuse. I emphatically refuse. So, anyways, hope you guys are all staying healthy, staying well, staying busy, and we'll talk to you soon.